Hello. I want to start off by thanking everyone for attending this last presentation of the last day of our conference in Las Vegas. So I know people are ready to go out. So I'm going to be talking about drift reduction for computer vision models. Just a brief introduction about myself. I'm working as principal engineer for AI in the Cisco Emerging Tech and Incubation Group at Cisco. And I'm also an author on MLA and Big Data on LinkedIn Learning. Just running through a quick agenda, we'll start with what is drift. I'm not sure how many people in the audience know around these areas. I'm just going to quickly cover through them, the types of drift, and how drift applies to computer vision applications, and what techniques are available to detect drift, and some of the best practices to cover in the next 20 minutes. So, what is model drift? And model drift is essentially when the predictive accuracy of models drift and decay over time, which is once you build a model with a specific accuracy, then deploy it in production, the model then starts, the accuracy starts going down in production due to various reasons, and that's what is called drift. Why is it important to monitor? Because we want to know if the models are continuing to perform as they should, and if they require retraining to kind of retrain with new data and get it back to the expected levels. So if you look at how the accuracy changes over time, so a training, you see you have three models here, model 1, 2, 3, all of them during training have a high level of accuracy. And they may take any of these patterns. So we start with model 1, which is decaying progressively as each month goes on. It's kind of gradually going down. Its accuracy went from 90 to 60%. Model 2, on the other hand, was holding you for about 2 months, and then it took a deep dive in just 1 month. So that is also possible, like a sudden drift. And third is a model 3, which is like, it's oscillating within a given threshold, and that's kind of okay because as long as it is within the thresholds, and that is not a drift. So that's a model that is doing okay. But we need to kind of monitor this over time and make sure that the models are working as desired. What causes drift? Why do models drift? The first reason is that the relationship between features and target may change over time. We always train models using data from the past, and that assumes a given relationship. And the business system changes, the ecosystem changes, because of which this relationship also may change over time, where some customers may be buying more than usual. Really, they are not buying that much, they'll start buying more. So there is a change in behavior that may trigger this. Feature distributions may change also. Like, in age group, for example, people are less than 20, who only have around like 20% of your overall customer base. All of a sudden, they become like 40% or 50% of your customer base. The feature distributions may change. That may change the behavior of the customers, which means your model may be inaccurate. And then there may be new data. It's possible that new variables are introduced in the data, that new feature variables are introduced in the source data. New values for classes may be introduced. Here you only have like 4 types of customers. The marketing team decided to squeeze in a fifth one, and your model is not ready for that. So you may be having new data and distributions. Similarly, for continuous variables, the mean, standard deviation, or the quartiles, they may all change over time. They may all indicate that there's something going on with the data that may cause drift and that may need retraining. It's also possible, and actually very much possible, that there is data capture and processing errors upstream. Any kind of data capture errors or processing errors in the pipeline, data processing pipeline, would also cause drift because the data then becomes inaccurate. That's going into the model, and that may lead the model to behave erratic also. So there are 2 types of drift. One is called the concept drift, which is essentially that the relationship between the features and target change over time. So the features, the distribution of the features remain the same, but the real world, the ground truth has changed, and that ground truth change has not been reflected in the model. And for example, let's say the feature variable is age group 30 to 40, and the conversion rate, ground truth, is the predicted value. So let's say in April and May, the ground truth is 20 to 24%, and then in June, July, the conversion rate bumps up to 43, 41% for this age group. But your model that is built based on the earlier data would continue to somewhere predict between 20 to 22% only. So that is a change in ground truth that is not reflected in the model. And this is a high, when this kind of thing happens, there is a high possibility of impacting a model's predictive accuracy and may require retraining with new data. The second type of data is drift is called feature or data drift. In this case, the distribution of values or classes in a feature changes over time. For example, here there is no target variable involved. Let's look at mean income as a feature variable. The mean income of all the customers who have in April may around 20K. In June, July, went up to 30K. It's a continuous variable. As a class variable, the percentage of men in the data set, in April and May it was like around 50%, June, July went down to 22%. So that's a change in the class distribution. These kind of distribution changes will also happen over time, and this may or may not impact a model's accuracy. It may not because, just because a given class variable is occurring more doesn't mean the model is behaving differently. The model, as long as it keeps the relationships intact, will continue to predict correctly. But this kind of change may be an indicator of a bigger problem, which we don't know, which is where we need to drive in and analyze. In all cases, whether it is feature or concept drift, we need a way to monitor drift and flag it. How do we detect drift? So there are different types of drift trends that you would notice. For example, there could be a sudden concept drift, like all of a sudden an abrupt change in the accuracy levels in production. Why would that happen? Root cause may be like changes in the ecosystem, product mix change, marketing scheme, something changed that has changed the behavior of the principles that are involved in the data set. There could be certain feature drift, which is a feature variable has an abrupt change in its distribution. That usually points to like equipment errors, like if you're getting data from cameras or telemetry, it's possible there's an equipment error that's causing this. It's possible there are data processing errors. It's possible that some new code introduced upstream may be changing the way that these variables behave, because it's not just the model that changes in production, it's also the data pipeline that changes, and they're putting in some new code that has some new bugs or there may be new features that could cause feature drift also. Gradual drift is when the drift changes slowly over time, and that is something that is very difficult to investigate. Deep investigation is needed with possibly the subject matter experts to understand what's going on in the market. A fourth type of drift is cyclic and seasonal drift. Drift increases during a specific time and then comes back to normal. And this is actually not a drift because it says that this is usually an indication that in your training data you are not accounted for some cyclic or seasonal variations, right? So weekend behavior or all this holiday behavior is not modeled correctly into your model, then you will see drift in this cyclic or seasonal fashion that's happening in your model. That's not technically not a drift, it's more like it's kind of more like you're missing out some feature variables that you interact. What kind of drift detection techniques are there? The inputs to drift detection are, of course, you need all the features. You need the predicted label and the true label. That's easy to say. And when you have both the predicted and true label known in production, you know, okay, this is what my model is predicting. And after some time, you also get to know the true label. Like if your model is predicting whether a website visitor will buy a product, and maybe after some time you know the website visitor did buy it or not. Then you know that there is, then it's very easy to measure because with both these variables you can compute like accuracy, effort scores, type 1, 2 errors, all of them. And then you can plot these variables over time on a month by month basis or week by week basis and say, how this is varying. Is it suddenly falling off? Is it maintaining within the threshold levels? You can do all of that. This is easy, but the problem is how many cases we know that where true label is always available in production. That's the biggest challenge. And if true label is available, this is really an easy problem to solve. When true label is not known, then you're going to be looking at the input data that is going in as an indicator for possible drift on the outcome. So when you look at input data, then you're looking at data distribution. Is there a change in class value percentages? Change in distribution of continuous data? Does this out of distribution data happening? Then you have all these statistical tests for distributions that are there that you can use to find if that there is drift happening. So these are general things that you apply for all kinds of models, classical machine learning, most probably. And what kind of drift reduction software is available? AWS, GCP, Azure, all of them on drift reduction tools that are integrated into their pipeline. You then have Cerner.io, Alibi Detect library that provides you drift detection features. Torch drift is there in PyTorch. Scikit-learn multiflow is the Scikit-learn package. Then TensorFlow data validation has drift detection. And there are, of course, a bunch of commercial offerings in ML labs. And you would have seen a lot of products in the exhibition around these areas. Moving on to computer vision models. What are the challenges that are there with computer vision models? The first one is you're dealing with images and videos. You're just dealing with a bunch of pixels, not with variables like age or income, something that's more meaningful. You're dealing with images. And these features are difficult to understand. It's not easy for you to correlate these features to a business thing and say, I did this in the marketing side and I see the impact here, I can understand the relationship. So that's one. The size of input data is huge. Features in classical machine learning, 10 features, 20 features, it's easy for them to find a drift by feature or trying to do any kind of comparison. Looking at an image, you have like pixels and pixels have RGB. So you got like in a high definition photo or video, you got like 2 million features there. It's very hard for any algorithm to even work on them and the kind of load it puts on the compute resources for that. So there is definitely a processing cost involved in drift reduction, and diagnosis of problems is also difficult. In the case of classical machine learning, you can say, here is this variable that is acting crazy because of why my model is messed up. Whereas in an image, it's not possible to diagnose these problems easily. And one of the bigger things that we've seen in computer vision models is that most of these are running on things like cameras, which kind of devices, which are edge devices. And because they are more prone to environmental issues, operational issues, like the camera might be like tilted, that may cause all your images to be messed up. Or you may have like connectivity issues because they are edge devices, wireless connectivity. You may have connectivity issues. So equipment malfunction is a huge problem in these places, because of which you will notice drift. So that problem has to be separately analyzed. Because a lot of times that will manifest itself as drift, and then you are just running crazy trying to fix the data. So, what kind of data you need for drift detection? Prediction and true labels, if that is available, that is great, because that is not a big set data set. Whatever be the image coming in, these are just two variables, very easy. And the same techniques that we talked about, accuracy, FM scores, is useful. But more cases, true labels are not available. That is the problem. In terms of features, you got to do something about these features because these are huge arrays of data. So you can standardize the resolution. That's one technique you would do to kind of standardize all of them to one standard resolution. Dimensionality reduction is a huge thing when it comes to computer vision. To reduce the dimension of data into a much manageable things like principal component analysis or simpler value decomposition. Those techniques are very useful in taking this huge arrays of data, reducing them to a few features, and then applying drift reduction on them. And the other thing that you can do when dimensionality reduction is not a guaranteed thing, because when you reduce dimensionality, it's also important that it retains the signals. And a lot of times it may not. So in those cases, another option is that when you're looking at a convolutional neural network, the initial layers are all convolutional and max spudding layers, which are essentially feature engineering. You finally get to the densely connected layers, which is where prediction happens. So the output of these convolutional layers that is going as input to the dense layers, that can be used as the final features. And those features are order of magnitude smaller than the initial input. So that is another option for you. And of course, you need the baselines from training data, which is what you would use to compare for drift reduction. Techniques for measuring computer vision drift. So you look at accuracy, where you have both predicted and true labels, efficient and effective. True labels availability is the issue. Again, you can have all these accuracy measures, F1, F2, and mostly everything, if both is available. If both are not available, then you have to look at other techniques which are more about comparing two distributions. So Kolmogorov's Monroe or KS is one technique where you take input as production data and training data and then provide as input, and that will then compare both these inputs and give you the output. So dimensional something to consider here, because it's trying to compare two data sets, huge data sets, and your algorithm will require a lot of compute power for that. So dimensional reduction is a useful thing. And a maximum mean distribution is another technique, again comparing two distributions statically. Or you can build your own drift reduction classifier. It's another, you build your own model to detect drift. So that requires an amount of training and everything, but if drift reduction is very important to you, then this is something that you want to build your own drift reduction classifier. So coming down to some best practices on computer vision drift, it's always recommended to build some models for equipment malfunction. I hope that the equipment manufacturer themselves start building these models so that it's easy to figure out, okay, it's not an equipment malfunction, and that can be ruled out when you notice drift. And then dimensional reduction is a huge thing. You have to try different techniques to see which technique is most suited for your model, such that even after reducing the dimensions, it still retains all its signals. So another thing is to wait for trends. A lot of people jump on when they see drift. First of all, when you're looking at drift, you need to make sure that you measure it at regular intervals. And at each interval, you need to have enough samples so you eliminate any kind of sampling error. And then you wait for trends, at least 3 or 4 data points to see whether the drift is staying down before saying that I'm going to get into retraining. So some patience is required. You don't have to wait too long. You shouldn't be also doing it very shortly. So that's something that you want to balance out. The bigger issue for drift computation is what kind of resources is needed, especially in computer vision models, rather than trying to find drift for every sample. Maybe you sample out take few samples from the production data and then only compute drift on it. That's another technique you can do. So to reduce cost, you're only doing it on samples. Edge cloud architecture, computer vision, a lot of the edge devices are deployed on the edge. So you could possibly think about doing things like dimensionality reduction on the edge device, so that you're not sending huge amounts of data to the cloud. They get used into the cloud to do just drift reduction. The challenge in drift reduction is how do you minimize cost, because it's a side activity. It's not your main inference activity. It's a side activity. You want to keep the cost as minimal as possible. So pretty much that's it.
We have some time for questions if anyone would like to ask questions. We have time for Q&A if you guys would like.
How much resources would you say is appropriate to dedicate to detecting drift and to writing for it?
Well, I think it's relative. First of all, the first thing you have to look at is what is your size of data. The size of data means what is a single sample size, like what is the single data size, and how much data size data is you generate. The next thing is you also want to minimize by using batch processing. You don't need, there's no need for real-time drift reduction, like live drift reduction. You can also start data and sample it and do it as a batch. Do it as a batch when your compute requirements are low, things like that. But that is the cost is a kind of, I don't think there is a straight answer for it. Depends on the model and how important that model's drift is. Depends on the application. And I think there's a lot of work happening. I don't think the algorithms you have today is optimized. And there's a lot of work happening to optimize these algorithms because trying to compare two sets of huge sets of data is not something that is scalable in the long run. So you want better techniques. So classifier is one way. If we could build that classifier in an auto-ML fashion. So you see that there's a lot of tools that are coming out and you see a lot of these MLOps tools. And some of them things they are working on is how could we do this drift reduction automatically rather than trying to do it model by model. It's possible that they can create a model that this counter model that can actually go and detect drift based on your input. I mean, I expect that this is a very new field, right? So it's going to evolve, it's going to mature, and there will be more mature techniques coming out. There's a lot of research going on in this space right now. Yeah. Actually falls within the MLOps thing. So, but then today, as you see that MLOps is becoming bigger and bigger as opposed to the model training itself, right? So yeah, it's an MLOps, part of MLOps, but if you are a small team, then most probably the same set of people are doing both, right? And again, best thing is to use out of the box things as much as possible. Right? There are libraries that are there. There is a lot of tools. You see a lot of demos here when they show it in Drift. So as much as possible, use them.